Thank you to the Math Society for resuming these talks, and thank you for the invitation, and for all of you for coming today. My talk comes right in the middle, so it's a little bit of an intermission kind of between the other talks. My talk is going to be less dizzying than the ones before, and in fact I'm going to talk about 7 times that mathematics has changed our view of the world. So the first one is when mathematics changed astronomy. In the past, the Greeks used to believe that the whole solar system, I mean, they only knew about planets up to Saturn, they all fitted within the distance that we know today between the Earth and the Moon. So it was pretty like a small, convenient solar system. But then Aristarchos came and he vastly expanded this view. So where does the mathematics come in? Well, he thought as follows. If you look at the Moon when it is half full, it must be the case that the angle between the Earth, Moon, and Sun, like that, must be at 90 degrees, right? Because that's exactly what causes it to be half full. So he thought, well, if I measure the angle between the Sun and the Moon, right, with his primitive protractor, so to speak, right, he'll be able to figure out exactly the type of triangle that we actually have during half full moon. And in fact, he did this, and he got a minimum amount of degree of 87 degrees. I mean, in actual fact, it's even more than that, but he just gave like a minimum figure for that angle. So if you then take the adjacent side, EM, in comparison with the hypotenuse, ES, right, that will give us the cosine of 87 degrees, which you can actually calculate, right? Well, they didn't have cosines at that time, but they did have equivalent ratios, and that ratio comes out to be 1/19. So that means the Sun is 19 times further away than the Moon. However, when you look at the Sun and the Moon, they look actually the same size, right? That's why we have eclipses, right? When one goes in front of the other. So if one is 19 times further away, but they look the same, that means it is 19 times as large as well, right? 19 times as large as the Moon. Well, by a different process, he found that the Moon is about 1/3 of the size, radius of the Earth. So that means that the Sun is about 5 times the radius of the Earth. So 5 times 5 times 5, that's 125 volume-wise as big as the Earth, right? So obviously it makes much more sense, he thought, right, that the Earth goes around the Moon, around the Sun, rather than the Sun, which is 125 times as large, going around the Earth. So this is where the heliocentric idea came about, right? So that's like the first time that actual mathematics, trigonometry there, made a big difference. And then I'm going to jump now to the Middle Ages. We've all seen rainbows, you know, some are big, some are small. But I don't know, maybe not everyone knows this, but the actual size of the circular arc, the angular radius, I mean, of that circular arc is always the same. It's always 42 degrees, right? Whether it's in the morning or in the evening or whatever, it's always 42 degrees. Now, Theodoric argued as well. So before him, they always thought, you know, that rainbows came about by some kind of reflection of the light of the cloud or something like that, right? There wasn't like any simple explanation for it. But he realized that, well, if it's due to water droplets, right, some kind of reflection of light and water droplets, then angles don't depend on size, right? You can scale up something and it will remain the same, similar, right, figure, and therefore the angles in that figure will remain the same. So he thought, well, why don't I try to expand, scale up a droplet of water and make it as large as I can possibly can. So he took a globe of glass, right? He filled it up with water, and that kind of made sense. That is like a representative of a water droplet. So when you shine white light through this globe of water, he could actually see carefully how it reflects and so on. And when measuring the angle between the incident rays and the outgoing rainbow there, the outgoing rays, he found exactly 42 degrees. So this was his explanation, right, why, in fact, rainbows occur, right, because of this phenomenon. So this was the first inkling that there's a lot of mathematics inside nature. Right? My next moment is when Kepler found that the orbits of the planets are ellipses. Now, how on earth did he find that, right? Well, he was the astronomer, the main astronomer of the emperor at the time, right, the Holy Roman Empire. And before him there was a very meticulous person, Tycho Brahe, who had kept data like this exactly for a whole decade. Right? He measured, painstakingly measurement every day, every night, right, where the sun is or where the planets are and so on for 10 whole years. And Kepler had all this data, and he thought he could do something with it. So he took a date, pick any date whatsoever, find where the sun is, find from that table there where the sun is directed at, which star kind of it's directed at on that day. That would give us this line over here. So if you go the opposite direction, that will give me the line where it intersects the circular orbit of the Earth. That will be exactly where the Earth is on that date. Right? Then on the same date, right, you pick on the same table there, you pick the direction of Mars, and that way you can draw a line in that direction. Right? And that will give me, somewhere along that line will be Mars. Now this is the brainwave that he had. He knew that Mars takes almost 2 years to go around the sun, one full revolution. So he ignored all these dates and he skipped 2 whole years, basically, from all this data. That means Mars is exactly back where it is, but on that date, you can repeat that same argument, right? You can find where the Earth is, and then you can find the direction of Mars, and therefore where they intersect with each other, that would identify Mars' position precisely. Right? In fact, since he had 10 years of data, he could repeat this 5 times, right? 2 years, 5 times. So you could have other positions of the Earth, and you can repeat this, and they all converge towards roughly the same point. Right? You can take the average position at that point. And then all you have to do is repeat this whole procedure, let's say a week after, and then a week after that. Right? And that way you start filling out the different positions of Mars, and it filled out precisely an ellipse. Right? So this is how he determined that particular configuration. How mathematics changed biology, anatomy rather. Well, when you open up a corpse, not that I've done this myself, but you'll find all the organs, and you'll find in particular the heart. And from the heart, you'll find 2 sets of vessels, right? The arteries and the veins coming out, right? And they seem to vanish into the body, right? Into the tissues. Now, in ancient times, the Romans and the Egyptians, they used to believe that the heart pumps blood through the veins, and air, they called it vital air, through the arteries. Right? So all the tissues would receive the kind of nourishment from the blood as well as the air. Right? That's what they thought, how the body worked. But then came Harvey, and he said, well, no, it's actually circulating, going around the arteries, then somehow vanishing through the tissues and coming back through the veins. But no one really believed him because they didn't have microscopes at that time. So they didn't know about capillaries or anything like that, so it didn't make much sense. Until he came up with this mathematical argument, where he said, well, if you look at the heart, the volume of the heart, that's about 2 fluid ounces. So every time it beats, it's beating 2 ounces per beat, times 72 beats per minute, times a whole hour. That will give us approximately 260 liters per hour. So the heart is pumping that much blood every hour. But of course, we don't have that much blood in us, right? That's an enormous amount. We only have 5 liters of blood. So it must be the case, kind of like all you have to do was QED at the end there, right? That there must be a circulation of the blood. The same blood is being circulated around and around. So that was the big revolution occurring in the 16th century. Right, the next one is how mathematics changed chemistry forever. This is due to Antoine Lavoisier, although I changed the situation slightly so that actually Lavoisier did not actually do this himself. But the idea is, what are materials made up of, right? What is the chemical formula for the compounds? How did they come up with these chemical formulas? Well, he reasoned as follows. He said, well, let's suppose I have some oil that you're burning, which I don't know the formula of. So he knew it's made up of carbon, hydrogen, and oxygen, but he didn't know exactly the exact ratios of those three elements. So let's call them M and K. So when you burn it, that's adding oxygen, and they're combining to give us carbon dioxide and water. But he was a very meticulous person again, and he weighed everything very carefully. So he got those numbers here. The original amount of oil was, let's say, 10 grams, and then he collected all the gas that comes out, and it came out to be about 30 grams, and the water again 12 grams, and you get three equations there in M, N, and K. Right? So three equations in those three unknowns give us the ratios of M is to N is to K as 16 is to 32 is to 1. So that's how he came up with these formulas. Right? In fact, at the beginning, these numbers did not mean exactly what they mean today, that you have an exact amount of 16 carbons, 32 hydrogens, and 1 oxygen. It meant a ratio of the carbons is to hydrogens to oxygen. Initially, that was the idea. Right, so that's how our chemical formulas started off. Nothing seems to happen here, so maybe that's this one. This is how mathematics changed geology now. In the past, people used to think that the Earth was created about 4000 BC. Right? That was like inherited knowledge, so to speak. But Charles Lyell in the 19th century, so not that long ago, argued that structures like Mount Etna were actually made up from lava, continual eruptions of lava, year after year after year. So he took, as a ballpark figure, he said, I can calculate the age of Mount Etna if I estimate the volume of Mount Etna as a cone, and then divide by a rough estimate of the rate at which Mount Etna gives out lava every year. So you just have to substitute the volume 1/3 pi r²h, right, for the cone, and divided by the rate, which he estimated as a cube, let's say, of 50 meters by 50 meters by 50 meters. Right? So every year there's that much lava. You all know that Mount Etna is very active, and every year it does erupt quite regularly. So he estimated that amount, and if you divide there, you get 4 million years rather than 4,000 years, right? So that's a big order of magnitude difference. And it started hinting at the really old age that we know of today, which is in fact another 1,000 added to that, right? So that's another big change in our perspective. And finally, the one of Mendel. Mendel was a mathematician, but he also loved plants, and was again a very meticulous person, and he planted thousands upon thousands of pea plants, and he cross-pollinated them, one by one. So you can imagine how patient he was. But he found the following: that if you have pea plants, which are all yellow peas that give out all yellow peas, and plants which give green peas, and you cross-pollinate them with each other, you get the first generation consisting of plants that give out only yellow peas. But then if you cross-fertilize these plants with each other, you get this interesting observation that you get 3 yellow is to 1 green. You always get that fixed ratio. Now, it's not easy to think up of why this would happen, but being a mathematician, he thought of the binomial theorem. And he said, well, of course, the first generation, it's easy to explain. It's just that the yellow wins over the green somehow. But then for the second generation, he thought of the binomial theorem, and you get y plus g squared. That will give you all the possible combinations of combining the yellow with the green. Right? You get yy, yg twice, and gg. And if y wins over g, then actually those first two terms will give me 3. Right? 3 yellows and 1 green. That explains the ratios that we found over here. So that was the origin of the inheritance laws of Mendel. Of course, there are many, many, many other possibilities I could have picked of how mathematics changed our whole view of the world, including art or philosophy or music, or indeed physics as well, right? There are many, many ways, but I just picked the ones that are easy to explain in 10 minutes. But I'll stop with with 2 slides here, how mathematics held back science, right? Not how it progressed science, but actually how it kept it back. And I'm going to pick just 2 of them. For example, geocentrism. Why didn't people believe Aristarchos actually that the Earth goes around the sun? Well, because if the Earth is rotating on its axis, a whole circumference every 24 hours, well, the circumference is 40,000 kilometers of the Earth. So in 24 hours, if you divide, you get 300 meters per second. So every single second that passes, we're actually going through 3 whole stadiums, right? The whole university, basically, right? Every single second. And obviously, at that time, people did not believe that we wouldn't notice this, right? So that was kind of like a proof that we're not actually spinning. The Earth is not actually spinning on its axis. So that's that. And another one would be, for example, Lord Kelvin, where he calculated the sun's age to be 10 to 20 million years using more advanced mathematics, which at that time, this is at the time of Darwin, was inconsistent with evolution. So there was a lot of debate that this can't possibly be the case, that you have really old years. And radio, the same thing, right? You all know that Marconi kind of invented radio, but Marconi invented radio against conventional wisdom that, electromagnetic waves travel in straight lines. So if you take a tangent at the surface from London, by the time it reaches New York, it will be thousands and thousands of kilometers high up, right? So there's no way it could possibly reach New York, but in fact it did, right? So, and finally, of course, there are many other times that mathematics was irrelevant completely to the discovery, including telescopes and microscopes. No mathematics was involved there, or printing presses, or the vacuum. And nowadays, large language models, although they use mathematics, but the weights themselves are not, they don't come up with those using some mathematical theory, right? They come with those using feedback and learning. People don't know what it's essentially a black box, but people don't know exactly what it contains. All right, so thank you all for your attention. Any questions? Yes?
I disagree that mathematics was irrelevant for grand buildings because
well, yes, I would agree with you, because obviously you have to use some mathematics in practically all of them sometimes.
Was built very mathematically, very rigorously.
Which one?
Perspective.
Perspective.
When designing buildings, people.
No, definitely. But you shouldn't underestimate the knowledge of master builders, right? Even though they weren't mathematicians, they could still build, using their experience.
The actual building, not the design of the building.
Well, I guess both, yes. Yes. Sorry. Yes.
On the previous slide, you mentioned that mathematics gave the horoscopes.
Yes, as well. Yes. Yes. At one point, around 2,000 years ago, in fact, astronomers became very adept at predicting where planets lie, right? I mean, if you tell me, for example, this particular date, they could find exactly where Mars is at that moment. So some of them made money out of this by predicting, by making horoscopes for people. It could tell you if the Caesar comes and he wants to know where the planets were when he was born, then yes, they could actually calculate that. But obviously, horoscopes then led to a whole field of astrology, and I'm sure that's kind of kept things pretty back quite a bit. Yes, Kenny.
So Kepler assumed that the Earth went round this in a circle.
He didn't assume it. He actually, but Earth is different from the others because since we're actually living on it, we have all the other planets that we can observe. He could, and we also have our seasons and everything. I mean, we have much better measurements for Earth than for Mars. So he could figure out the orbit of Earth, and the orbit of Earth is very much circular. Yes. The only difference between a circle and our Earth's orbit is that the Sun is not exactly at the center. It's eccentric. That's why where eccentricity comes in. And it's not exactly at the center, but apart from that, it's practically a circle. Right. Thank you once again.